This video, we'll be discussing about Physics Paper 2, AS Level Structure Question 2024, May June, Variant Day is 21, and the subject code is 9702. Number 1. So, the drag force acting on an object falling through air is given by this expression, where A is the cross-sectional area, V is the velocity, rho is the density, and C is the constant called the drag coefficient. So, drag coefficient is C. Use SI base units to show that the drag coefficient has no unit. So we need to show that the drag coefficient has no unit. So first of all, we need to make drag coefficient becomes a subjective formula. So drag coefficient is equal to 2FD by rho A V square. So force is a unit of force. So FD is the force. So force is equal to mass into acceleration, and the unit of mass is kilogram, and for acceleration it is meter per second square. So kilogram meter per second square. And for density is equal to mass by volume. So mass has a unit of kilogram and volume has a unit of meter cube, and since it is divided, so negative meter cube. So kg and kg cancels, then so meter per second square at the top divided by meter to the power negative 3, meter to the power negative 3, and since the base is same, so we need to add the power. So minus 3 plus 2 plus 2 and minus second to the power negative 2. So second to the power negative 2 cancels each other out. Then meter divided by minus 3 plus 2 plus 2, that is meter. So it cancels and the overall unit becomes 0. So it is shown that the drag coefficient has no unit. Part B, figure 1.1 shows a sphere falling at a terminal velocity in air. So the sphere is falling at a terminal velocity in air, and since it is falling at a terminal velocity, so terminal velocity is a constant velocity, and since velocity is constant, so velocity is constant or velocity is same. Since velocity is same, so we know that acceleration is equal to change in velocity by change in time, and here it is terminal velocity. So terminal velocity means that the velocity is same. So the velocity is same, therefore the velocity is not changing. So since the velocity is same, so it is not changing, therefore the change in velocity is 0 divided by time. So we can see that the acceleration becomes 0, and since acceleration is 0, so resultant force, that is F net, is equal to mass into acceleration, and since acceleration is 0, so the resultant force is 0. So as the object is falling at a terminal velocity, that means the resultant force is 0. That means force downwards must equal to the force that is upward. So assume that the upthrust on the sphere is negligible, so there is no upthrust. On figure 1.1, draw and label arrow to show the direction of the two forces acting on the sphere. So we need to show the direction of the two forces. So first of all, the weight is acting vertically downward from the center. Since it is an uniform object, so the weight is acting vertically downward from the center. And drag force. So drag force is a resistive force that resists the motion. So drag force is a resistive force, that is the drag force acting on the object falling through air. Since the object is falling downward, so the drag force must act upward. Since it is the resistive force, so the drag force is acting upward, and this arrow must have the same length as the weight. There is drag force have the same length as the weight. Then the mass of the sphere is 49 gram. Calculate the drag force acting on the sphere. So drag force. So we have found that the terminal velocity, the velocity is same. Since velocity is same, so acceleration is 0. Since acceleration is 0, so the resultant force is 0. So downward force is equal to upward force. So the downward force is equal to the upward force. So it cancels and the resultant force becomes 0. So the downward force, that is weight, is equal to the upward force Fd. So weight is equal to Fd. So we have given the mass. So we need to find the value of drag force. So we have given the value of mass, and we need to find drag force. So by using weight is equal to mass into gravitational field strength. So 79 gram. So 49 gram. So we must convert 49 to kilogram. That is 49 by 1000 kilogram into 9.81. That is the gravitational field strength. And you have to remember that the gravitational field strength for physics is 9.81, and for mechanics it is 10 meter per second square. So by using the equation, we calculate the value of weight. since we know the value of weight, so weight is equal to drag force. So weight is equal to drag force. So weight is equal to drag force. Therefore, the drag force is 0.48 Newton. Then the sphere is falling in air at a terminal velocity of 25 in SI base units. So terminal velocity of 25, and since it is velocity, so it has a SI unit of meter per second. That is, the sphere is falling at 25 meter per second. The density of the air is 1.2 in SI base unit. So density is mass per kilogram. So mass has a unit of kg and kilogram has a unit of meter cube. So divided by, so it is divided, so meter to the power -3. So density, we know the value of, so first of all, we know the value of velocity, density, and the diameter. So this is the diameter. Now calculate the drag coefficient C. So we need to find the value of C. So initially we make the C becomes the subjective formula from this formula. So by using this equation, we need to substitute the value of the velocity. So we have given the value of velocity, then the value of density, and the diameter. So by using the diameter, first of all, we need to find the value of area. So since it is a sphere, so it is a circular object. So for circular object, area is pi r square. So pi r square, or for diameter it is pi d square by 4. So pi r square or pi d square by 4. So we know the value of diameter. So pi d square by 4. So we know the value of velocity, that is 25. We found the area, and we know the value of density. And what is the value of force? Fd. There is a drag force. Drag force is 0.48 Newton. So 0.48 Newton. After substituting the values, we calculate the value of C as 0.4527. There is approximately 0.45 to two significant figures, and it has no unit. C has no unit because here we have found that C, or drag coefficient, has no unit. Therefore, we have given our answer as 0.45. Question number 2, part A. Define velocity. So velocity is the change in displacement by change in time. So velocity is a change in displacement per unit time, or change in displacement divided by change in time. Then a student throws a ball over a vertical wall of height h meter. So the height of the wall is h. This is h. So the height of the wall is h, as shown in figure 2.1. The ball leaves the hand of the student at a height of 1.2 meter above the horizontal ground. So the ball leaves from a height of 1.2 meter. Then the ball has an initial velocity of 22 meter per second at an angle of 40 degree to the horizontal. So the ball has an initial velocity of 22 meter per second at an angle of 40 degree. So since we have given the value of velocity, so by using this, we can find the velocities, horizontal and the vertical component of the velocity. So by using the 22 meter per second and 40 degree, we can find the horizontal and the vertical component of the velocity. So the horizontal component would be, so since it is a right angle triangle, so the horizontal side is cos and the opposite is sine. So horizontal is 22 sine 40 and opposite is 22. Horizontal is, that is the adjacent is 22 cos 40 and the opposite is 22 sine 40. So the opposite is 22 sine 40. So we break the velocity into its component. Then the wall is horizontal. The wall is a horizontal distance of 36 meter from where the student releases the ball. So the distance from the wall to the student is given as 36 meter. Air resistance is negligible. That means as the ball is moving, there is no air resistance opposing its motion. So there is no air resistance. Determine the time taken for the ball to reach the wall. So we need to find the value of time for the ball to reach the wall. So to find the value of time, so we have given the value of velocity. So we know the value of distance, that are the distance values. So we can use the formula velocity is equal to displacement by time. So velocity is equal to displacement by time. So the value of time is equal to displacement by velocity. So time is equal to displacement by velocity. And to find the value of time, So here we have given the value of horizontal distance. So the horizontal distance is 36 meter. So we can use the horizontal distance and the horizontal velocity to solve this problem. So the horizontal distance is 36 meter and the horizontal component of the velocity, that is horizontal component of this velocity, is 22 cos 40. So 22 cos 40. So by substituting the value, we find the value of time, that is 2.136, that is approximately 2.1 to two significant figures. Then calculate the vertical component u of the initial velocity of the ball. So what is the vertical component? So for the vertical component, we know that by using the right angle triangle, cos theta is equal to, so vertical component. So vertical component is a sine. So sine theta, let's consider the angle as theta. So sine theta is equal to opposite, it is opposite by hypotenuse. So we need to find this opposite side. So opposite side is equal to sine theta into hypotenuse. So the value of hypotenuse, that is, this is the hypotenuse, that is 22. So the hypotenuse is 22 and sine theta. So we have given the value of theta as 40. So sine 40. That means our opposite side, or this side, that is the vertical component of the velocity, is 22 sine 40. So the vertical component of velocity is 22 sine 40. And if we just calculate, then it will be 14.14, that is approximately 14 meter per second. Then the ball just goes over the wall. Calculate the height of the wall. So the ball goes over the so the ball goes goes above the wall, over the wall. So the ball goes just over the wall. That means from this point. So we can say that the height from where the ball goes is approximately equal to the height of the wall, because it is given in the diagram, that is, they are equal. So how can we find the value of height? So we can use the distance formula, that is S is equal to ut plus half at square. So by using this formula, we can solve this problem. And so for this part, I want to add something, that we can use S is equal to ut plus half at square in this formula also. But here we can see that we know the value of initial speed, that is the initial speed, that is 22 cos 40. So 22 cos 40, and the value of, so we know the value of distance. So we need to find the value of time. So the time is t, and we have given the value of distance, that is 36 meter. So this is 36 meter, and we have the horizontal velocity as 22 cos 40. So horizontal velocity is 22 cos 40 into time plus half at square. And here we can use this formula also, and it would give the same answer as given, because here acceleration is 0. Why acceleration is 0? Because in the horizontal direction, suppose for the ball moving in the horizontal direction, so the ball is moving in the horizontal direction and there is no force opposing the horizontal direction, because the air resistance is negligible. Since the air resistance is negligible, so there is no opposing force in the horizontal direction. So since there is no opposing force, so the horizontal velocity remains the same. Since the horizontal velocity remains the same, so the acceleration is 0. That means in the horizontal direction, since there is no force acting in the horizontal direction, suppose the ball for this point, so there is no forward force at this point. For example, the ball at this point, the ball is already being thrown. So the ball is thrown from this point, and now the ball is at this point, and the ball is already being thrown. So now at this point, there is no forward force acting on the ball, because it is already being thrown. Since there is no forward force acting on the ball, also since air resistance is negligible, so there is no backward force. There is no forward force acting at this point, and there is no backward force acting on the ball. So the resultant force in the horizontal direction is 0. And since the resultant force in the horizontal direction is 0, so acceleration is also 0. So acceleration is 0. After substituting the value, we can calculate the value of time as 2.1. Now for this part, that is the height. So S is equal to ut plus half at square. So now we need to calculate the value of vertical height. So for the vertical height, there is this vertical height. So we need to consider the vertical component of velocity, and the height is h, and the time taken to reach the wall is 2.1 second. So from this second to this wall, whether in the horizontal direction or in the vertical direction, the time is same. That is from this point to this point, the time taken is 2.1 second. So we know the value of time, we consider the height as h, and we know the vertical component of velocity, that is 22 sine 40. So s is equal to ut plus half a t square, where the initial component of velocity, that is the value of u, is 22 sine 40, and 22 sine 40 is 14. So 14, and the time is 2.1 second. So the value of time to reach the wall is 2.1 second. So ut plus half at square. So what is the value of acceleration? Now for this ball in the vertical direction, so for the ball in the vertical direction, we know that the weight is acting vertically downward. Weight is acting vertically downward, and for air resistance, since air resistance is negligible, so there is no other force that is acting in the vertical direction. So only weight is acting, and since only weight is acting, so weight is equal to mass into acceleration. So here the acceleration is acting is the gravitational field. So gravitational field, and the gravitational field downward is 9.81 meter per second square, and for upward movement, it is negative 9.81 meter per second square. Since here we can see that the ball is moving from this point to upward, since the ball is moving upward, so the acceleration is negative 9.81. So we need to consider acceleration as negative 9.81, and after substituting these values, we calculate the value of distance, that is s is equal to 7.8 meter. Now we calculate the distance as 7.8 meter, and this distance is from this point. So from this point to this point, that is from this point to this point, the vertical distance. And sorry. So from this point to this point, the vertical distance. So this vertical distance, and we need to find the total height. So the total height is this vertical distance plus 1.2 meter. So this vertical distance plus 1.2 meter, because we calculate the height from the initial position, to the final position, that is this is the initial position and this is the final position. So we calculate this value of height, and the total height, that is h, is equal to this value of height plus this value of height, that is 1.2 meter. So we need to add 1.2 from this value. We need to add 1.2 with this value to calculate the total height as 9.0 meter, that is 1 2. So it is two significant figure. Question number 3 part A. State the principle of conservation of momentum. So by principle of conservation of momentum, first of all, we know that momentum is equal to mass into velocity. So for principle of conservation of momentum states that the momentum before collision is equal to the momentum after collision. Since the momentum is conserved, as it is conserved, so obviously the momentum before collision must equal to the momentum after collision. Then for part B, an object of mass 2m is traveling at a speed of 5 meters per second in a straight line. It collides with an object of mass 3m, which is initially stationary, as shown in figure 3.1. So the object of 2m moving at a speed of 5 meters per second, and the 3m is at rest or is stationary. And so this is before collision. After the collision, the object of mass 2m moves with a velocity v at an angle of 30 degree to the original direction of motion. So original path is the horizontal direction, but the 2m mass after collision, so this is before collision and this is after. So after collision, the 2m mass moves with a velocity v at an angle of 30 degree. So since it is moving at an angle, so we need to find its horizontal and the vertical component of velocity. So the horizontal component is v cos 30, that is for a right angle triangle, the horizontal side is cos, so v cos 30, and the vertical is v sin 30. Similarly, the object of mass 3m moves with a velocity w, also at an angle of 30 degree as shown in figure 3.2. So the mass of 3m is moving at a velocity of w. Since it is moving at a velocity of w, so the horizontal component is w cos 30 and the vertical component is w sin 30. So this is after collision. Now, by considering the conservation of momentum in 2 dimensions, calculate the magnitude of v and w. So we need to find the value of v and the value of w. So first of all, to find the value of v and w, so since momentum is conserved, so the momentum before collision is equal to momentum after collision. So before is equal to after. Before is equal to after. But here we can see that initially the object is moving horizontally, and after the collision the object is moving vertically. So before is equal to after for horizontal, and before is equal to after for vertical. So first of all, for horizontal direction, we equate before is equal to after. That is, we know that momentum is equal to mass into velocity. So mass into velocity before collision, that is 2m into its velocity, that is 2m into 5. So 2m into 5 plus 3m into 0, since the 3m at rest. So before collision, the 3m mass is at rest, so the initially it is at rest, so the velocity is 0. Then after collision, and we are now considering the horizontal direction. So after collision in the horizontal direction, so the 2m is moving at a speed of v cos 30. So moving at a velocity of v cos 30. So mass into velocity, that is momentum is equal to mass into velocity. So 2m into v cos 30, 2m into v cos 30 plus m into v w cos 30. So the mass 3m into w cos 30. So 3m into w cos 30, and this is not m, this is 3m into w cos 30. So this is for before is equal to after for horizontal direction. And since we need to consider the two dimension, so horizontal and for vertical. So for vertically, here we can see that initially there is no vertical component of velocity, or there is no vertical movement. Since initially there is no vertical movement, so before the vertical movement is 0, or the momentum in the vertical direction is 0. So the momentum in the vertical direction is 0, and after the collision we can see that the vertical movement occurs. So momentum after collision in the vertical direction, that is 2m into v sin 30. So 2m into v sin 30 plus 3m into w sin 30. Now here we know that one is moving upward while the other is moving downward. So if we consider the upward movement as positive, then obviously we need to consider the downward movement as negative. So the movement downward is negative, that is negative. So that is the movement downward as negative. So the downward movement is negative. So upward movement is positive. So if we consider the upward as positive, then downward is negative. So the downward is negative, so we place a negative sign. So if we then solve, then 2m v sin 30 is equal to 3m w sin 30. So 3m w sin 30. Then after solving, v is equal to 1.5 w. Then we need to substitute the value of v in this equation, that is for the horizontal direction. After substituting the value of v, that is 1.5 w, after substituting the value, we get the value of w as 1.924. There is approximately 1.9 as the value of w. And what is the value of v? So we need to substitute the value of w in the equation for v to find the value of v as 2.9. So we get the value of v as 2.9. So this is for 3 part B. Now for 3 part C, an object of mass 4.2 kg is traveling in a straight line at a speed of 6 meters per second. So initially it has a speed of 6 meters per second, and the mass is traveling in a straight line. That is, the mass is traveling in a straight line at a speed of 6 meters per second. That is initially. Is brought to rest. That is, the final velocity is 0 in a distance of 0.050 meter. So the distance s is equal to 0.050 meter, and this is the initial velocity. Now calculate the magnitude of this force. So we need to find the value of force. So force is equal to mass into acceleration. So we know the value of mass, that is 4.2, and what is the value of acceleration? So to find the value of acceleration, first of all we need to use the initial velocity. We know the value of initial velocity, that is 6 meter per second. Final velocity is 0, and the distance is 0.050 meter. So by using the equation v square minus u square is equal to s, so we know the value of final velocity, that is 0, initial velocity is 6, and the distance is 0.05. So what is the value of A? Acceleration is negative 360 meter per second square. So we know the value of acceleration is negative 360 meter per second square. So the acceleration is negative 360 meter per second square. So after substituting the value in the equation for force, we get the value of force as 1512 Newton. That is approximately 1500 Newton to two significant figures, and it is negative. Now, here we can say that the force we have written here is positive, because here we can see that the object of mass is traveling in a straight line. The object is brought to rest. Since the object is brought to rest, suppose the object is moving in this direction, and since the object is brought to rest, that means there is some resistive force. Since there is some resistive force that causes the object to be rest, and since it is a resistive force, so it is obviously negative. So the resistive force is negative, but when we write the value as the value of force, so we have to write 1500 as our answer. So the force is negative, but for the resistive force is positive. So the value of force is negative. So the force is negative. But since it is resistive force, so obviously the resistive force would be positive, because the resistive force itself is negative. The resistive force would be positive because the resistive force itself is negative. So whether it is positive or negative, we know that resistive force itself is positive, that resistive force itself is negative. Since the resistive force itself is negative, so we don't need to mention a negative sign. So the answer is 1500 Newton. And here are the three questions that is the you can use, that is S is equal to ut plus half at square, v square minus u square is equal to s, and v is equal to u plus at. So these are the equation for motion. Question number 4 part A, define strain. So strain is the extension divided by original length. So strain is the extension divided by original length. Where a copper wire of length 4 meter has a uniform cross-sectional area. So we have given the value of cross-sectional area, a tensile force of 18 Newton. So we have given the value of force, and we have given the value of length. So this is the length, this is the area, and this is the value of force is applied to the wire. This causes the wire to extend by 1.4 millimeter. So we have given the value of extension, that is the x, and since we know the value of extension but it is in millimeter, so we must convert this to meter. Up to its limit of proportionality, calculate the Young modulus of the wave. So we know that Young modulus is equal to stress by strain, and we know that stress is equal to force per unit area divided by strain. Strain is the extension divided by original length. So force per unit area, and since we convert divide into multiply, so length and x would reverse. So length comes upward and x comes below. So force into length. So force into length by area into extension. So force, so we know the value of force, divided by area, so we know the value of area, and the original length is 4 meter. And what is the extension? So we know that 1 meter is equal to 10 centimeter, and 1 cm, 1 meter is equal to 100 centimeter, and 1 centimeter is equal to 10 millimeter. So 1 meter is equal to 1000 millimeter. So 1 millimeter is equal to 1 by 1000 meter. So 1 by 1000 meter, or 10 to the power minus 3 meter. So 1.4 millimeter is equal to 1.4 into 10 to the power minus 3 meter. So 1.4 into 10 to the power minus 3 meter. So after substituting the value, we get the Young modulus as 1.1 in 10 to the power 11. So 1.1 in 10 to the power 11. And you have to also remember that Young modulus, for maximum amount of time, that is the extra term, that is 10 to the power 11 comes. So that means there is a value at front, suppose 1.1 or 2.2 or 9.3, and it is obviously multiplied with 10 to the power 11. That is, when 10 to the power 11 is given, then we have to we know that it is Young modulus. It is for maximum time, it is Young modulus. And for chapter 1, that is physical quantity and units, and for estimation, you have to know that for estimation of Young modulus, suppose you have given two values, suppose 1.1 into 10 to the power 19, 1.1 into 10 to the power 12, and 1.1 into 10 to the power 11. Then what would be the Young modulus? So Young modulus would also obviously be 10 to the power 11. So since 10 to the power 11 is this, so this is our Young modulus. So Young modulus is multiplied with 10 to the power 11. Now for part 2, on figure 4.1, draw a line to show how stress varies with strain for a wire up to its limit of proportionality. So stress against stress and for up to its limit of proportionality. So stress against strain up to its limit of proportionality. And since the wire does not reach the limit of proportionality, and this is the point of limit of proportionality, there is limit of proportionality. So before limit of proportionality, the graph have to be a straight line. So this is a straight line graph passing through the origin. So straight line graph passing through the origin. So whether it is a stress strain graph or a force extension graph, that is force against extension, the limit of proportionality is from the origin and it is a straight line. So from the origin and it is a straight line. And this is the limit of proportionality. For part C, a second copper wire has the same length, so the length is same as the wire in B, but a larger diameter. So the diameter is large, and since we know that area is equal to pi d square by 4, and since the diameter is more, so the cross-sectional area is more. So for the second wire, the cross-sectional area is more, that is area is more. Now both wires are subjected to a tensile force of 80 Newton, so the force is same. By placing a tick in each row, complete table 4.1 to compare the stress and the strain for the two wire. So stress. So what would be the stress? So we know that stress is equal to force per unit area. And since the value of force is same for both the wire, so it is same. And for the second wire, we know that the cross-sectional area is more. Since the diameter is more, so the cross-sectional area for the second wire is more. So since the cross-sectional area is more, that means the denominator is more. Since stress is equal to force by cross-sectional area, since the denominator is more, so the numerator have to be less. So the stress have to be less. That is, for the second wire, the stress is less, and for the second wire, what would be the strain? So we know that strain is equal to extension divided by original length. And since the original length is same, so what would be the extension? So here it is not given any value of extension, but we know that Young modulus is equal to stress by strain. So Young modulus is equal to stress by strain, and we know that stress is equal to force per unit area divided by strain, that is strain is equal to extension divided by original length. So force per unit area into length by extension, and since the force is same, that is 18 Newton, and the original length is also same, that is for the second wire the length is same, so length is same, but for the second wire, we can say that the area is more, so the diameter is more, so the area is more, since the area is more. Now for the Young modulus, so Young modulus is always a constant, so it is constant, or the Young modulus is same. Since the Young modulus is also same, force is same, and the length is same, so if the area increases, the extension must decrease. Because if we just rearrange, then the equation would be that extension is equal to force into length by area into Young modulus. So area into Young modulus, and force is same, length is same, Young modulus is same. So if the area increases, then the extension obviously decreases. So the extension for the second wire is less. Since the extension is less, so the extension value is less. So strain is equal to extension by original length. Since the extension is less, so the strain for the second wire is less. So the strain for the second wire is less. 5. A stress string PQ has a length of 1.2 meter. So PQ has a length of 1.2 meter. One end of the string is attached to a vibration generator. So one end is attached to a vibration generator, that is, this is the vibration generator, and the other end is attached to the wall, as shown in figure 5.1. The vibration generator is switched on. So the vibration generator is switched on, and a stationary wave is formed on the string. So the vibration generator is switched on, that is, the generator vibrates, and a stationary wave is formed on the string. Now you have to remember that the wave that is produced is a stationary wave and not a progressive wave. The string is shown at one instant of time in figure 5.2. So this is the string at one instant. Explain how the stationary wave is formed between the vibration generator and the wall. So how the stationary wave is formed? So wave from the vibrator, wave from the vibration generator. So wave from the vibration generator is reflected by the wall. So wave is reflected by the wall. The incident wave and the reflected wave superimpose to form a stationary wave. So the wave from the vibration generator is reflected by the wall. So as the vibration generator vibrates, so the wave from the vibration generator is reflected from the wall. And as the waves reflected, so the incident wave superimpose with the reflected wave. So as the incident wave superimpose with the reflected wave, and thus a stationary wave is produced. So the wave from the vibration generator is reflected. You have to remember that it is reflected. So it is reflected from by the wall, and since it is reflected, so incident wave and the reflected wave superimpose to form the stationary wave. And what is superposition? So superposition or superpose by principle of superposition. So the principle of superposition states that when two waves, so when two or more waves meet at a point, the resultant displacement at that point is equal to the sum of the individual displacement of the individual waves at that point. So the principle of superposition states that when two or more waves meet at a point, the resultant displacement, so resultant displacement is equal to the sum of the individual displacement d1 and d2. So the principle of superposition states that when two or more waves meet at a point, the resultant displacement is the sum of the individual displacement. So resultant displacement is the sum of the individual displacement. Then calculate the wavelength of the stationary wave. So we need to find the wavelength. So here the total distance is given is 1.2 meter. So the total distance is 1.2 meter, and to cover this total distance, this is one wave produced and half the wave produced. So one wave is produced, one lambda is produced, and half lambda is also produced. So one wave that is from this point to this point, and half wave that is from this point to this point. So in total, 3 by 2 lambda is produced. So 3 by 2 lambda or 3 by 2 wave is produced. That is 3 by 2 is 1.5 lambda is produced. So 1.5 lambda is produced. So what is the value of lambda? Lambda is 0.80 meter. So 0.80 meter, that is 0.80 meter, that is approximately 1, 2. So 2 significant figure. And lambda, that is the wavelength, is 0.80 meter. So this is 1 lambda and this is lambda by 2. So this is covered in 1.2 meter. For part C, figure 5.3 shows the stationary wave at time t is equal to 0 when all the points on the wave are at their maximum displacement. So when all the points are at their maximum displacement, the period of the wave is 0.16 second. So the time period is 0.16 seconds. On figure 5.3, sketch the shape of the stationary wave at time t is equal to 0.24 seconds. So what is the sketch of the wave at 0.24 seconds? So you have to remember that this wave is a stationary wave, and for a stationary wave there is no movement at the nodes. So the nodes remains at their position. So there is no movement at the nodes while the antinodes move. So for 0.24 seconds, so for 0.16 second, we know that for 0.16 second, the antinode moves from the top to the bottom and then again move to the top. This is for 0.16 second. Now for 0.24 second, so for 0.16 second, so as one complete wave is produced or the time period, so it moves to the bottom and again move to the top. So it has covered 0.16 seconds. So 0.24 minus 0.16, we get a time of 0.08. So what is the movement now for 0? So what is the movement for 0.08 second? So first of all, for 0.16 second, it moves down and again move up to complete one wave. Then it covered 0.16 second, and for 0.08 second, so it moved. So for 0.16 second, first of all, so 0.16 second, it moved down from the topmost point to the down. So from the topmost point to down, then again down, then up, then again up. So here we can see that this topmost point is moving downwards and then upwards. So downward and then upward. So this total time is 0.16 second. That is from this point to this point, that is 1, 2, 3, 4. So for four movements, the total time is 0.16 seconds. So for one movement, what is the time? That is 0.04 seconds. So one movement means that from the topmost point to this point is 0.04 seconds. So from the topmost point to this point is 0.04 seconds, and for 0.08 second, it moves from the topmost point to this point, that is 0.04, plus an additional 0.04, that is from this point to an additional 0.04 seconds to the bottom point. So now here we can see that it moves to the bottom point. Now if we just draw the points, then antinodes have no movement, while for the nodes have no movement. So nodes have no movement. Now for the antinode, so this point moves from the topmost to this point at 0.04 second, then again 0.04 to this point. So now the antinode is this point. Similarly, this antinode at 0.08 second moves to this point. So this point, then this antinode is at this point. So if we just join the points, then the displacement would be like this. So this is the movement of the wave at 0.24 seconds. Nodes have the movement, and for 0.16 second it completes one wave. So after completing the one wave, it moves to down and again up. So from down to up, it comes to its original position. Since it comes to its original position, so it is now at this position. Now for additional 0.08 second, so additional 0.08 second, so this movement is 0.4, then again 0.4 to complete 0.8 second, and now this is at this point. Similarly, this point, the bottom point is at this point, and this point 1, 2. So at this point, so after drawing, we get this diagram. Then point R and T on the string are a horizontal distance of 0.30 meter apart and in positions as shown in figure 5.4. So R and T. State the phase difference between the oscillation of point R and T. So what is the phase difference? So what is the phase difference between R and T? So remember that, so this is the stationary wave. So for stationary wave, there is nodes, 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 and nodes, and the topmost point is the antinode. So as we can see that point R and point 2 T are separated by a node. Since the points are separated by a node, so the phase difference would be 180 degree. This is an important thing, that when the 2 points are separated by a node, the phase difference is 180 degree. Now let's suppose if the 2 points are within the same node, that is this node, and the 2 points are within the node, that is within the node. So since the 2 points are within the node, so the phase difference have to be 0 degree. But let's suppose if the 2 points are separated by the node, that is this node, if the 2 points are separated by the node, then the phase difference is 180 degree. But if let's suppose the 2 points are within the node, that is suppose for this node, if the 2 points are within the node, then the phase difference is 0 degree. Similarly, right now point R and T, so point R and T are separated by a node. Since the points are separated by a node, so the phase difference is 180 degree. Then state the speed of the progressive wave of the straight string. So we need to find the value of speed. So v is equal to f lambda. So v is equal to f lambda, and what is the value of velocity? So we need to find the value of velocity or the value of speed. So what is the wavelength or an information? So we have given the time period, that is the time period, and we know that frequency is equal to 1 by time period, that is 1 by 0.16. So frequency is equal to 1 by time period, that is 1 by 0.16, that is 6.25 Hertz. So we know the value of frequency. Now what is the value of wavelength? So what is the value of wavelength? Now for the wavelength, so we know the value of wavelength, that is 0.80 meter. So the wavelength for the wave is 0.80 meter. So the wavelength is 0.80 meter. After substituting the value, we get a speed that is 5 meter per second, 5.0 meter per second, to significant figure. For question 6 part A, state Kirchhoff's first law. So first law is the conservation of charge, and the second law is the conservation of energy. So for the first law, since it is the conservation of charge, so the sum of current entering a junction equals to the sum of the current leaving the same junction. Suppose this is a junction and the sum of the current, that is I, is entering a junction, so the current that is leaving the junction is also I. So the sum of the current entering a junction is equal to the sum of the current leaving a junction. And for the second law, we know that EMF is equal to the sum of the potential difference, that is EMF of the battery is equal to the sum of the potential difference V1 and V2. So EMF is equal to V1 plus V2. And for the first law, the total current entering a junction is equal to the total current leaving the same junction. Then a cell with internal resistance R is connected to two resistors R1 and R2 as shown in figure 6.1. The potential difference across R1 and R2 are V1 and V2 respectively. The terminal potential difference of the cell is V. So the terminal potential difference across this is the terminal potential difference, and terminal potential difference is always across the terminals of the cell. So this is our cell, this is the internal resistance of the cell. So this is our cell and this is the internal resistance of the cell. So this is our total cell, and the terminal potential difference is across the terminals of the cell. So across the terminals of the cell, so use Kirchhoff's law to show that the resistance R of the external circuit is given by this expression. So R is given by this expression. So first of all, so here we know that from Kirchhoff's second law, that is total EMF we consider as V. So total EMF is equal to V1 plus V2. So total EMF is equal to V1 plus V2. That is, we know that V is equal to IR. So total current, that is IR total, is equal to IR1 plus IR2. And since the current entering a junction is equal to the current leaving a junction, and for series circuit, we know that for series circuit the current remains the same. For series circuit the current remains the same. So since the current value is same, so we can eliminate I from the equation, and here we can see that RT is equal to R1 plus R2. So by using Kirchhoff's second law, EMF is equal to the sum of the potential difference. So EMF is equal to sum of potential difference, and we know that voltage is V is equal to IR. So V is equal to IR because R is equal to V by R I. So V is equal to IR. So after substituting the values, we cancel the value of I because in series circuit the current is same. So R total is equal to R1 plus R2 as shown. For part C, the EMF of the cell in figure 6.1 is 1.5 volt. So we have given the value of EMF of the cell. That is, for the cell, the EMF is 1.5 volt. And so we know the value of EMF. The value of R1 and R2 are 10 ohm and 15 ohm respectively. The terminal potential difference of the cell is 1.35 volt. So the terminal potential difference is 1.35 volt. And what is terminal potential difference? So I have discussed that the terminal potential difference is potential difference across the terminals of the cell. Terminals of the cell, so this is the cell. So the terminal potential difference is given, that is 1.35 volt. So calculate the internal resistance of the cell. So we know that the total EMF is equal to the terminal potential difference plus the potential difference across the internal resistance. So you have to remember the equation, that is EMF is equal to terminal potential difference plus the potential difference across the internal resistance. So, and this is usual because the EMF of the cell is equal to the terminal potential difference plus the potential difference across the internal resistance. And what is terminal potential difference? So terminal potential difference is the total potential difference across the terminals of the cell. So terminal potential difference, so terminal PD plus the potential difference across the internal resistance, this internal resistance. So EMF is equal to potential difference across this internal resistance plus terminal potential difference. So EMF is equal to terminal potential difference plus internal potential difference across internal resistance. So what is the potential difference across internal resistance? Potential difference across internal resistance is equal to EMF minus terminal potential difference. So we know the value of EMF and the terminal potential difference. So if we subtract, we get the potential difference across the internal resistance. So we know the value of potential difference, that is V across the internal resistance. So we know the value of V across the internal resistance, and we need to find R. So we know that R is equal to V by I, and we need to find the value of R. We know the value of V. Now to find the value of R, first of all we need to find the value of current. And you have to remember that since this circuit is a series circuit, so our circuit is a series circuit, and for series circuit the current is same, that is I. since the current is same, that is I, so we can use any of the information to calculate the value of current. So what is the value of current? So we have given the value of R1 and R2. So by using the value of R1 and R2, we can calculate the total resistance. Because here we know that R total is equal to R1 plus R2. So R total is equal to R1, that is 10, and R2, that is 15. So the total resistance of the whole circuit is 25 ohm. So we know the value of total resistance across the terminals. So we know the value of total resistance. So the total resistance, that is R1 and R2, and so we know the value of total resistance. So the total resistance across the terminals, that is, we know the value of total resistance of R1 and R2. And since R1 and R2 are at the terminals of the cell, that is at the terminal of the cell, and we know the value of resistance. So what is the value of terminal potential difference? So the value of terminal potential difference is 1.35 volt. So we know the value of resistance, that is 25, that is across the terminals, and we know the terminal potential difference as 1.35. So current is equal to voltage by resistance, that is, we know the terminal resistance across the terminals of the cell, that is this terminal and this terminal resistance, total resistance, and we know the value of terminal potential difference. So by using this, we can calculate the value of current. So current is equal to voltage by resistance. So current is equal to voltage by resistance, and the terminal potential difference is 1.35. So 1.35 by resistance. So the resistance that we get is 0.054 ampere. So the current that we get is 0.054 ampere. So now we know the value of current, and since the current in series circuit is the same, so we know the value of current, and we have initially found the potential difference across the internal resistance. So what is the resistance of the internal resistance? So resistance is equal to voltage by current. So we know the potential difference across the internal resistance, and we have found the value of current. So we can substitute the values and find the resistance of the internal resistance as 2.777 or approximately 2.8 ohm. So the internal resistance is 2.8 ohm. That is, this internal resistance is 2.8 ohm. D. The resistor R3 is added to the circuit in 6.1. So R3 is added to the circuit in 6.1. So that the circuit as shown in 6.2. So this is the overall circuit after the third resistor is added. This is our initial circuit, and now a third resistor is added. So this third resistor is added. So state and explain the effect, if any, of this change on the current of the cell. So what is the effect of this resistor on the current? So as we can see that as the third resistor is arranged in parallel, so since the resistor is arranged in parallel, so you have to remember that as the resistors are arranged in parallel, so the total resistance decreases. Since the total resistance decreases, so the current must increase. And why the total resistance decreases? Because for parallel combination, we know that 1 by R total is equal to 1 by R1 plus 1 by R2. And let's suppose all the resistors have a resistance of 2 ohm. So 2, 2, 2. So initially, when these two resistors are connected, so the resistance total is 2 plus 2, that is 4 ohm. When these two resistors are only connected, so that is 4 ohm. But now, since an additional resistor is added, so what would be the total resistance? That is 1 by R total is equal to, so R1 is the addition of this two, that is 1 by 4 plus 1 by 2. So if we just calculate, then R total is equal to, so the R total is 1.3333 ohm. That is, as we can see that since an additional resistor is arranged in parallel, so since an additional resistor is added to the parallel, is added in parallel, so as additional resistor is added in parallel, so as the additional resistor is added in parallel, so the total resistance has decreased. Since the total resistance has decreased, so the current of the cell must increase. So for parallel combination, for parallel combination, if we add some additional resistor in parallel combination, so the total resistance as we can see, has decreased. So total resistance have to decrease and the current must increase. Then terminal potential difference of the cell. What is the terminal potential difference? So we know that EMF is equal to terminal potential difference, terminal PD, plus potential difference across internal resistance, potential difference across internal resistance. So terminal potential difference is equal to EMF, terminal potential difference is equal to EMF minus potential difference across the internal resistance. Terminal potential difference is equal to EMF minus potential difference across the internal resistance. So as we can see that what happens to the terminal potential difference of the cell. So as we can see that initially the current has increased as the total resistance is decreased due to parallel combination. The current has increased, and since current is increased, so we know that terminal potential difference V is equal to EMF minus potential difference across internal resistance, that is IR. And since I smaller, that is I smaller across the internal resistance, and as we can see that current has increased, so potential difference across internal resistance. So as current has increased, so obviously the resistance is same. So since the resistance is same and the current has increased, so this resistance value is same. That is the resistance value same and current has increased. Since current has increased, so the potential difference across the internal resistance increases, and since the potential difference across the internal resistance increases and the EMF is same, so EMF minus potential difference, so EMF is same but the potential difference increases. Since the potential difference across internal resistance increases, and so EMF minus potential difference would give a lower value. Therefore, the terminal potential difference must decrease. So as the current increases, as we can see that the total resistance has decreased due to parallel combination, so the current increases. And since the current increases, so potential difference across the internal resistance is equal to I smaller. Since current increases, so potential difference across internal resistance increases. Since potential difference is equal to I smaller, so potential difference increases. And since potential difference across internal resistance increases, so EMF minus potential difference is the terminal potential difference. And since we have to subtract a bigger value, so the final answer is small. Therefore, the terminal potential difference is less. As current has increased, current increases. Therefore, I smaller increases. Since the resistance of the resistor is same, so the potential difference across internal resistance increases. So EMF minus potential difference is a terminal potential difference. So the terminal potential difference must decrease. So as current increases, potential difference across the internal resistance increases, and as potential difference across the internal resistance increases, so the terminal potential difference decreases. Question number 7. Nuclei of an isotope of copper has 29 proton and 37 neutron. So 29 proton and 37 neutron. The isotope is beta minus emitter. And what happens in beta minus decay? So for beta minus decay, neutron changes to a proton. Neutron changes to a proton. Beta minus particle is emitted, and with beta minus particle, antineutrino is emitted. So with beta minus particle, antineutrino is emitted, and with positron or beta plus particle, neutrino is emitted. So with electron or beta minus particle, antineutrino is emitted, and with positron or beta plus particle, neutrino is emitted. And obviously, energy is also emitted. Now, state the nuclear notation in the form of AXZ for this nucleus of copper. So X is the symbol for the element. So the element is copper. So copper, there is copper, and A is the mass number or the nuclear number. So mass number or nuclear number is the number of protons plus neutrons, and Z is the atomic number or proton number, that is the number of protons. So mass number or nuclear number is the proton plus neutron, that is 29 plus 37 is 66, and the atomic number or proton number is 29. So we have expressed this. Now the energy spectrum of beta minus radiation emitted by a sample of this isotope is shown in figure 7.1. So number of beta particles and kinetic energy of beta particle. Use figure 7.1 to explain why other particles apart from beta minus particle are emitted during this decay. So as we can see that kinetic energy of the beta particle is have a continuous range. Now you have to know that for beta minus particle have a continuous range of kinetic energy. Continuous range of kinetic energy. So beta minus particle have a continuous range of kinetic energy, while for alpha particle, if let's suppose there is an alpha particle, then alpha particle has a discrete amount or the same amount of kinetic energy, so it would be a straight line. For alpha particle, they have the same amount of kinetic energy, but for beta particle, they have a continuous range of energy. Why they have a continuous range of energy? Because if we see the equation, then for beta minus decay, as we can see that neutron changes to a proton, electron, or beta minus particle, antineutrino and energy. So here we can see that with beta minus particle and antineutrino is emitted, and so the energy is divided between beta minus particle and antineutrino. So with beta minus particle and antineutrino is emitted, so the energy is shared. So this energy is shared between beta minus particle and antineutrino. So the energy of the decay is fixed. So the total energy is fixed. So the total energy is fixed, but since energy of the beta particle have continuous range of values, because with beta minus particle, with beta minus particle, that is beta particle, and antineutrino is emitted, and so the energy is shared between beta minus particle and antineutrino. So the energy of beta particle have a continuous range of values. So beta particle have a continuous range of value, and antineutrino must possess the remaining energy. So the total energy is shared between beta minus particle and antineutrino. Therefore, beta minus particle have a continuous range of energy. So the total energy is shared between beta minus particle and antineutrino. So since the energy is shared, so obviously the beta minus particle have a continuous range of energy. State the name of the other particle emitted during this decay of the isotope. So as we can see that neutron changes to a proton, beta minus particle or electron, and an antineutrino. So an antineutrino is emitted. So another particle that is emitted is antineutrino. Then the copper isotope decays to an isotope of zinc. Give the radioactive decay equation for this decay. Include the nucleon and the proton number of all the particles. So initially we know that copper has a symbol of copper 6629, and copper is a beta minus emitter. So here, since it is a beta minus emitter, so 1 neutron from copper changes to proton and beta minus particle. So first of all, copper, that is 6629 copper, changes to zinc plus beta minus particle plus antineutrino. And since copper is a beta minus emitter, so neutron changes to a proton. That means now the proton number has increased by 1. For zinc, the proton number must have increased by 1. So as we can see that for this is the proton number, and for zinc the proton number has increased by 1, plus beta minus particle is emitted and antineutrino is emitted, also energy is emitted. So neutron changes to a proton, beta minus particle, antineutrino and energy. So copper changes to a zinc, beta minus particle, antineutrino and energy, and here neutron changes to a proton, and since this is a nuclear number, so proton plus neutron, and since 1 neutron has 1 proton, here we can see that proton has increased, so neutron changes to a proton. Neutron changes to a proton, so the sum of the neutron and proton is same. So the number is 66 and 30. So this is the overall equation.